Good morning, friends. This is 𝗘𝗍𝗺 and I would like to thank every one of you joining me today in this session. This session is focused on mainly on the analog design. However, I will talk about whatever analog design is and on a large scale of VLSI, and in this session really this is a very good platform where analog design and overall the VLSI design concepts and everything is getting introduced, and this is mainly for the awareness towards the community, towards the mainly for the students community. So this is this platform encourages me actually, and then I thought, okay, let me go back and then give something some introduction to analog design, because I feel that analog design is an unknown, probably not that much of well-known domain in terms of career perspective. So I will talk about it a bit more. However, all my talk, all my slides or whatever content I will be sharing is based on my own capacity. I will be I am basically from Cadence, Hyderabad. I am working there, but I will not go into details of anything, let's say the products or maybe the flow and from Cadence. So this is let me start in that case, and when I'm starting, I will actually want to start with my own examples, right? I mean, when I started back in 2000, early 2000 or late 1990, how I got into this field of analog design, and probably from there I will take you through what we are currently doing, and I will also share with you how you can look at this particular domain, how you can prepare for this domain, and then you can take a next step towards it. So when I started, let's say in back in 90 later stages and all, that time we were having this, let's say radios, tape recorders, and then televisions with the CRT, cathode ray tubes and all. So that was really interesting. We are not having any mobile, we are not having any mobile phones. So that was kind of like the instruments where we were getting exposed more towards the electronics things, and then we used to like this, we used to really enjoy those things. But again, the more enjoyment for me was not the front screen but the back of the instrument, which is the the back side. Like when the back side got opened and I used to look at those the internal to those devices, I used to see, okay, there are very much small components, right, with multiple colors, multiple structures sitting together, forming a nice musical harmony kind of stuff, right? So it was the starting point where I started my interest towards electronics, and then from there I get into the engineering on electronics itself. I was very much interested with circuit design, circuit theories, and from there, once I completed a bachelor's, I actually went into master's, and then there I get into this VLSI design and then analog design. So why I'm trying to tell is my interest actually take me from starting to where I am today. Now earlier at that point of time there was not much, there is probably today, even today also, we do not talk much about this analog design field. So today in this opportunity I thought, okay, let me take this opportunity and then share with you what exactly the analog design is, and generally sometime, right, I mean I come across this kind of questions, right, or this kind of queries from my friends, my colleagues, not my colleagues are aware, but friends and relatives and all around me, that what I'm generally doing. So the thing is, what I'm doing is nothing but the same. It's similar to what you can, if you can look at from the point of view of let's say a kid playing a kind of like a Lego toy, or maybe the puzzles, right, where jigsaw puzzles and all, right. So when I look at those, right, I actually can easily relate to what I am doing even today. So if you look at this part, right, even today, I will definitely explain you what exactly I meant. When I'm starting, I will actually want to start with my own examples, right. I mean, when I started back in 2000, early 2000 or late 1990, how I got into this field of analog design, and probably from there I will take you through what we are currently doing, and I will also share with you how you can look at this particular domain, how you can prepare for this domain, and then you can take a next step towards it. So when I started, let's say in back in 90 later stages and all, that time we were having this, let's say, radios, tape recorders, and then televisions with the CRT, cathode ray tubes and all. So that was really interesting. We are not having any mobile, we are not having any mobile phones. So that was kind of like the instruments where we were getting exposed more towards the electronics things, and then obviously we used to like this, we used to really enjoy those things. But again, the more enjoyment for me was not the front screen, but the back of the instrument, which is the the back side. Like when the back side got opened, and I used to look at those the internal to those devices, I used to see, okay, there are very much small components, right, with multiple colors, multiple structures sitting together, forming a nice musical harmony and kind of stuff, right. So it was the starting point where I started my interest towards electronics, and then from there I get into the engineering on electronics itself. I was very much interested with circuit design, circuit theories, and from there, once I completed a bachelor's, I actually went into master's, and then there I get into this VLSI design and then analog design. So why I'm trying to tell is my interest actually take me from starting to where I am today. Now, earlier at that point of time, there was not much, there is probably today, even today also, we do not talk much about this analog design field. So today in this opportunity, I thought, okay, let me take this opportunity and then share with you what exactly the analog design is. And generally sometime, right, I mean, I come across this kind of questions, right, or this kind of queries from my friends, my colleagues, not my colleagues are aware, but friends and relatives and all around me, that what I'm generally doing. So the thing is, what I'm doing is nothing but the same. It's similar to what you can, if you can look at from the point of view of let's say a kid playing a kind of like a Lego toy, or maybe the puzzles, right, where jigsaw puzzles and all, right. So when I look at those, right, I actually can easily relate to what I am doing even today. So if you look at this part, right, even today, I will definitely explain you what exactly I meant by it, but it's like the same fundamental things, that same kind of activity that we see around, and same thing we are doing there, but in a different form. So I will take you through that particular form, what we are doing. Let's say what analog design is, how analog design is getting into a particular electronic circuit, and how that electronic circuit is going into our applications, right? So that's how I'm going to take you through this a bit more, and then once I'm probably maybe you are free to ask me questions. I'll be more delighted to interact with you and answer or probably respond to your questions. That's where I want to have more interest. So there, maybe once I'm done, I will open it up, or maybe there are you can call me in that there are the numbers are flashing on the screen, so feel free to call me and then we can interact also. So let me start with this short story. Let me go into the larger story and then take you through this session. So I'll start with what analog design is, and I will also talk about the agenda of this, like basics of analog IC design, challenges, trade-offs, what exactly we face, tools and methodologies. I will go very much high level on these tools and methodologies. I will not go in details. There are several literatures available. So case study, practical application, emerging trends, conclusion, takeaways, and definitely interaction. So and then the entire discussion is mainly meant for educational purpose. So that's what I have added there as well. So let's start. What is analog design? So when we are talking about analog design, we are actually in a kind of like a continuous world where we interact, right? So let's say the interaction that I am doing today with you, I am doing in an analog fashion, but the way it reaches to you, right, through a media, right, there is definitely some kind of interface, like from analog to digital and again analog. So this is what I meant by what is analog design, right? So anything continuous, right, anything like there is like real time, you see something real time, you see around you, everything is analog, and that analog signal or analog quantity or analog entity is coming into a kind of like an interface, and that interface is actually the analog design, right? Now you take that signal, right, and then you put it into the electronics. Electronics will do some kind of processing, some kind of some kind of activity there, and that is going into a digital part. Now that digital part, right, is getting converted. So there are kind of like interface from analog to digital to analog, and in between analog and digital we talk about mixed signal. Now analog, digital, mixed signal, everything today is coming under overall VLSI, for which we are now talking in this platform, VLSI awareness, right? So analog, mixed signal, digital, all together it's forming in the VLSI domain. VLSI is very large scale integrated circuit. Very large scale integrated circuit. Now what we are talking about integrated circuit, if you think about integrated circuit, what I was giving an example 20 years back, that all those small components sitting on a kind of like a board and forming some kind of end application, maybe a tape recorder, maybe a radio box, or maybe a television box, which is like the bigger one with the CRT tubes and all, right? So those components are getting miniaturized and then embedded into a small particular chip. Now, friends, the chip means like we generally have, in our real life, we go for buying chips. That chips are different. I'm not talking about those chips. Here I'm talking about chips which is kind of like in a very hard form, like a kind of like a hard disk, if you can relate to it. Maybe nowadays it is not that much available, but earlier, maybe 5 years, 10 years back, we actually have the disk the compact disc, the DVDs, the CDs, like that kind of form, that kind of solid form of CDs, right? Now those, imagine that as a kind of like an example, and on similar kind of stuff, right, we actually do in silicon, and silicon means like the material is silicon, and inside that particular silicon based disk, we incorporate all those small components, like whatever we see in a big box earlier days. Those components are getting into that particular silicon, and then that is getting used in multiple applications. So that's what it is. I mean, today we talk about integrated circuits or ICs in that form. So everything comes together in a small box or a package, and that ICs are kind of like used everywhere nowadays in all these compact devices like mobiles, like this like let's say CPUs or GPUs, CPUs again central processing system, or many of these applications today we are talking about, right? And I will take you through some of these applications also. So here if you look at my screen, and in this place you can see there are I mean coming from the same side, right, like semiconductors or ICs. There are two types, digital and analog, and these are the ICs that I am talking about. These are the boxes, or maybe a kind of like a package part of it, and the entire design is going inside this, right, in a small silicon kind of like a structure. Now there are two types, one is digital, the other was analog, and today I am going to talk about analog. Now digital, if you look at it, it's a lot like millions or billions of transistors, right, transistors or components coming inside this. However, in analog we don't talk about that much of quantity. We don't say that okay, there are several millions or billions of transistors integrated and then forming an end application. No, analog is a kind of like it does not deal with so many transistors, but maybe sometime 10 to hundreds, and that's it, not even more than that. However, there are other challenges, right, with analog, because as I said, analog is continuous and it is real time, it is in the environment, so it is exposed to the environment. So it has several challenges, and those challenges are nothing but environmental challenges, the interference challenges, like noise will come in to that particular analog content, the other things, right, let's say the environmental factors, temperature, the other point, there are several things, right, which I will definitely take you through and give you some kind of idea about that. So this is the challenge, right? I mean, analog design is exposed to those interference, like all these environmental conditions, because it is exposed. It is actually very much, you are taking from the real world, you are actually taking the signals. The signal sometimes is very, very tiny, mainly for maybe medical applications. Some of the signals are very, very tiny, very small magnitude, so you have to take it and make sure that it is not getting contaminated with anything else. So these are challenges. I will take you through the challenges. Now, again, as I said, I will also take you through some of these examples that I mentioned in terms of Lego game, or maybe a kind of like jigsaw puzzles game and all those stuff. I will, whenever I will share with you these things, I will try to relate to those cases. Okay. So I have mentioned some about analog, and then in this particular page you can see there are some components in the analog design, like PLL, power management, band gap, data converters and sensors. So as I said, like you take the real time signals, put it into your design, and then in that design you have Legos, you have small blocks. Those are actually identified for specific application. Let's say PLL is a phase locked loop. It's a kind of like a Lego small block. Then power management, there are some blocks for power management. For battery power management, your power is going down, your battery is going down, and the circuit should sense it and then give you some alert, and you will go and then charge it, right? So these are the power management part of the circuit. It does that kind of closed loop management. Then band gap. Band gap is a particular term that we use to get a very stable reference voltage, right? And then again, voltage and currents. In this particular session, I will majority of the time I'll talk about voltage and current. Now, these are again very much known terms to majority of us, but when you talk about voltage and currents, right, we talk about, okay, the current is very high and you can get shock, and then don't put your fingers on the wire and all those stuff. Those are basically in high level. But when I'm talking about miniaturized, like millions, like very much small designs which are getting into those packages, the voltage and currents levels are also lower. I mean, it's not like that we are familiar with, but again, concept will remain same, that there is a voltage and there is current, right? So we have to deal with them, right? Voltage and current. So entire design. So that's the thing. So data converters, again, analog to digital and digital to analog. It's again a kind of a small Lego part which you can use directly. You can take it, take one of the A to D converter, analog to digital converter, which is ADC, digital to analog converter, and put it in your design, and it will do the job. It will take the signal, it will convert into digital, and the digital will go into the processor, and there will be some kind of processing happening. So again, right now, let's say if I as I have explained what is analog, now what is the role of analog? Obviously, the role is immense, and this role will always be there. It's a perpetual requirement. I mean, until unless we tomorrow we say that, okay, let enough of electronics, let's keep electronics back, let's go back to the life which we used to handle, we used to live 200 or maybe 300 or 400 years back. Until we are taking that step, right, analog requirement is perpetual. There is no end to it. We definitely need analog, because everything in the real world you need to take and then put it into a media and then use that media for particular application, right? So definitely there is a lot of demand of analog design, lot of demand of awareness to the analog design, and it will continue everlasting. One of the example, I will now take you through some of the examples, right? Let's say where exactly we talk about analog, what is the interface we talk about analog, and where it is needed. Quickly I will not read through everything, but just for your understanding, signal conditioning and interface. As I said, signal conditioning is needed for, let's say, you want to sense the temperature, you want to read temperature, right, in a thermometer, right, and nowadays it's everything digital thermometer, right, that mercury based thermometers are no longer available. So in the digital thermometer, you sense the temperature, convert it into a kind of like a form where you can read it, right. So there is something happening internally. What is happening? It's actually taking the signal, conditioning the signal, understanding the value, putting it in there for your reading. Now in some cases there are some controls. If let's say the temperature of a particular control system inside a car, right, the car engine is much more hot. So what is happening? It's sensing the car engine temperature and then doing some control and putting the engine with a coolant, or maybe it's maintaining the temperature in that way. So there's definitely some signal processing is happening. That processing is happening in the digital domain. Okay. So excuse me. Next one is on the power management. So again, as I mentioned, there are power management applications, right, and then power management, right, if you look at it, this is a battery, then you have some kind of small blocks here, and then the outcome is going to, again, this is again analog and this is also analog. So this power management is mainly for maintaining the power throughout the entire application, right. One thing is maintaining the balancing the power properly across all the components. Like maybe some part is taking more power, some part is taking less power, so you want to balance them, right? And let's say you are not using the device, you need to turn it off, so you need to make sure the battery is preserved. So then you have to make sure that there is a kind of like a mechanism that will make sure that the power is not getting consumed. So all those stuff is called power management, and this is again analog is indispensable there, and we definitely need analog kind of circuitry to read the power, to control the power, to control the fluctuations on the power, so that your circuit, your silicon, your devices, right, is not getting damaged. So power management is definitely having a lot of requirement. Signal processing, even in the digital signals, right, digital systems, right, we use analog signal processing, and there are some advantage for analog signal processing. Is mainly analog signal processing, it's continuous in time, so the latency through which the signal processing happens is faster, it's having a low latency. So many cases, even though in a complex digital systems, we use analog, and then the analog is again required there. Communication systems, right? So communication system is again, we are pretty much today when I'm talking, we are talking through a communication system only, and in this system, it seems like we are talking and you are in front of me and I'm talking to you, but generally it's not the case, right? It's actually many things are happening. So first thing that what is happening is the signal which is going from me, right, is actually in an analog interface. It goes to a kind of like a transmitter, and then from the transmitter it goes through a channel. There is a different sort of channel, and then from the channel it goes to again to your end, to the receiver, and then there are some kind of processing happening, and then that is getting converted to you as a signal again, right? Maybe a visual signal, maybe an audio signal, and that's how we are talking about. So communication systems is again, without analog it will never happen. I mean, definitely we need it. Obviously there are multiple frequency range, radio frequencies one, right, maybe in some other things. Healthcare application. So obviously as we move on, we see advanced healthcare, right, and the healthcare is again without analog healthcare is not going to happen, because healthcare things are mainly related to our body signals, right? Whatever the body generates the signals, maybe from the heart, from the mind, from any part of the body, right? These signals are again, it's continuous in nature, it's very tiny, it's very small, right? So we need to take these signals through some sensing mechanism and then amplify those signals and then take those signals into the next level to process. So definitely analog is there, and in that case like biosignals, medical imaging, all those examples are shown here. There are some kind of diagrams that which talks about these signals are coming from the body in multiple parts, getting into these ICs, and these ICs are all analog. It does some application, some kind of amplification, filtering, and then again some other kind of like operations it does, and then finally we get into the digital processing system, and then that will come as a display, as a report, and whatever it is. But finally the thing is analog is definitely a major part in the healthcare applications. Real-time processing, again this is kind of again what I said, that everything is the real time, and let's say directly taking the sensors, putting the sensors into a system. The image that shows here is of a kind of like a Arduino system, where we are taking all the sensors, like all these small pieces are sensors modules, and those we are putting into this Arduino systems and do some kind of end application there. So these are the major things which we talk about, which are very much familiar to us. We see everything every day, we deal with it, we touch it, right? And there analog is there, analog part is there. Now this so what I'm trying to say is analog is one thing that we cannot avoid. We definitely have to deal with it, right? Now let's see, I mean, now as we see that okay, analog is indispensable, analog is needed, what exactly analog circuit means, right? And why, I mean, let's say how these analog circuits, right, are getting dealt with, right? I mean, circuits means connecting all those components and finally getting an outcome, right? But how you do it, what you need to know to do it, right? And how you actually, you know, take it to your goals, to your career, how you actually learn about it. I mean, this is a huge field, this is a vast field. Even today, I mean, when I started learning from my school days, like as I said, right, looking into all those electronic component from the back side of all those instruments like tape recorder or radios, I started learning from there. Even today, I am still learning. So analog is such a field that there is every day you will learn new things, new challenges, new requirements, right? New kind of like inventions, right? So this is where analog is interesting. Okay, so now let me take you through that part. What I mean, right now I have given you an introduction of overall what is analog, how the analog is sitting into VLSI, right? And then I will go to components. If you, I mean, broadly, there are two kind of components, right? I mean, you don't have to probably remember so many things in order to do something in this, right? So there are broadly two kind of components. One is active device, right? Devices, like components means like you take all the small devices and then connect them in a multiple way and then create the overall architecture, right? Overall structure. Now that's what I was telling. So every places you can relate it to a kind of like a kids game, right? Which the way they do it, right? Like they take small building blocks, put it into a structure, and they have something in mind. They try to capture it in that particular structure and then try to see whether it is matching or not. So similar to this, right? You take all these components, transistors, resistors, capacitors, inductors, right? These are the components existing. Now how these kind of components are getting into a silicon substrate, right? Silicon substrate, I already told, right? Compare the silicon substrate with a kind of like a compact disc, right? A CD or a DVD, right? A kind of like that kind of structure which is very solid, and then inside that all those components will be laid in, right? So I will take you through that, how to do that slightly in a very high level. And like active devices and passive devices. Active devices, transistors, PMOS, NMOS, bipolar, passive, resistors, capacitors, inductors. Now in this particular image, if you look at it, left side there are some colorful drawings, colorful structures. These structures are nothing but devices, like active devices. These are called MOS. Now there are multiple structures like planar, FinFET, gate all around. Now these devices are nothing but you can see, imagine this as a kind of like a switch, right? And where the current passes through from left to right here, and then the gate used to turn it on and turn it off. So here if you look at it, this device, right, is the component, the building block. So you need to understand how this device work, right? So you need to understand, you need to go into not every detail but basic details of how this device work, right? Some device physics understanding, and then you have to understand from planar why we are going to FinFET, what exactly is this FinFET means, and then what exactly is this gate all around mean. So this is like device level understanding we need to have in order to form an analog circuit. We don't need, again as I said, we don't need a very detailed understanding of devices, but we need at least what are those devices, what it does, what is its basic characteristic, and all those stuff is good enough for us. The right side is showing it's the same thing. If you take a PCB, printed circuit board, right, there you can see some kind of wires been drawn, some kind of components been fabricated or attached to it, right. All those things, when we do a design, we draw like this. Now this is actually drawn in a kind of like in a computer, in a tool, where this one is the transistor, this one is an inductor, and they are connected in these two fashion. Now why I will connect an inductor, why I will if I connect a resistor instead of an inductor, what will happen, why I will not be connecting a resistor here, right. These are again depending on our requirement, depending on what we are doing, what we are targeting, what is our end goal, and then you can play with these connections, right. This is a bit more details, basically as I said, why this kind of devices are used. These are very small nanometer scale of devices or micrometer scale of devices. Just for your understanding, micrometer means like if you have a 1 meter length, right, and you cut that 1 meter into 1 million pieces, right, what you will end up with each piece is 1 micrometer. Now nanometer, today we are talking about nanometer. All these devices that you see here, they are in nanometer scale, tens of nanometer scales. So 1 micrometer, which you have cut this 1 meter stick into maybe 1 million times, right, and then each piece you cut it in 1000 times. So whatever you end up with, right, if you can imagine, it is beyond my imagination anyway. So if you can imagine that, is that one we are talking about here. So this one, what we are doing, we are basically taking a model of this device, right, because this is physically you cannot touch, you cannot even think of it, right. So you take the model of this device and then you put that model here, right, in equation form. Y equal to mx plus c. Y is the output, x is the input, c is a constant, right. So this is a kind of an equation which is first order, but for this device properties, right, for this device input output characteristics, this model is not that easy. This model is pretty much longer, pretty much complex, and we are getting these models from the who are creating these devices, right. So that's not what analog designers do. Analog designers take that Lego block, take that small particular model, take that model and put it into a kind of like a tool and run that tool with additional components, and then see what is the input versus output. That's what the concept is. Now again, these are the resistors, inductors and capacitors. This is what you can touch, you can see. If you open, let's say, please don't go and break your instrument at home. Please don't do that, but in case if you get a chance, please take a look. I really love to look at these things. Like this is the resistor, this is the inductor, this is the capacitors. In VLSI, all those stuff is getting into the silicon substrate in this form, right. This is the form that where it goes in. You will not be able to do these things there because these are bigger in pieces, and today when we are talking about is we have very much miniaturized electronics devices which are implanted inside someone's body, right. We are actually talking about very small instruments, very small or compact instruments. So this will not work there, right. So this is getting converted into this kind of structures, right. And here are some drawings, right, as I have shown you that okay, how we do design, right. So we do design in this fashion. We take one transistor model, another transistor model, connect it in this fashion. So this is again kind of like a ready-made, let's say ready-made structure that you are taking from the library. You have such kind of structures available in the library. You take it ready-made, and for a specific application, here we are talking about current mirroring. Mirroring means you have one current in one branch, you want the exactly same current in another branch, you do a mirroring, right. It's a kind of like an operation that you are doing by connecting the devices in this fashion, okay. Now similarly, there is another form which is differential amplifier. So again, in order to understand this, first what I mentioned, you need to have an understanding of device, not in detail into the device physics, but at least device characteristics, right. And then from the device you need to understand circuit theory, right, circuit basics, right, what is KCL, what is KVL, these are all related to current and voltage, related combinations and all. So you need to understand that, you need to go into a bit detail on that, right. And then with these two, right, device circuits, you can actually now read what are these components are, right, what are this current mirror, what is a differential pair, and then what are those components like common source, common drain, common gate, right. These are all like structures, right, which is used for specific purpose, right. So you should be knowing what is the purpose that I should be using it, what is the advantage, disadvantages of these structures. There are definitely switches, right. Switches is definitely needed because you have to turn on, turn off some part of it, right. Without turning on and turning off, right, you cannot perform some operations, right. So you definitely need to understand what kind of switches we have, we can make out of it, what kind of switches like can be used. If I look at it here, there is NMOS switch, transmission gate, CMOS switch. So I will not go into detail on this transmission gate, right. There are definitely advantage, disadvantage of transmission gate. There is CMOS switch, right. Again, these are all different sort of structures. If I go through it, I am sure I will need maybe not only few hours, few days, few weeks time to talk about it. As I said, it's really vast, and there is no end to it, right. And even today, as I said, I'm learning every day new things in a new platform, in a new technology, in a new environment, in a new challenging sections. Again, this is another quick snippet that you can see, guys, that this is like single stage differential amplifier, OTA. OTA is operational transconductance amplifier, two-stage amplifier, folded cascode amplifier, telescopic cascode amplifier. So again, rail to rail amplifier, and then comparator. So these are the components, right, when I talk about amplifier, right. So this is again, as I said, analog signals are coming, continuous signal getting amplified, because these signals are very small, right. If I directly give these signals to the digital part, digital won't be able to take it, because digital does not know where the signal lies, right. Digital has only two things, one is on and off. So I have to define this small signal such a way that the digital should be able to understand how to take this signal, right. So definitely I need amplification, I need to put it into a kind of like a analog to digital converter, and then give the digital to the digital part. Okay. Analog layout. Okay. Again, as I said, these signals beg your pardon. So this is not signal, I am talking about components. So these components that I have shown you as a kind of a model, if you see just one line and another line, 3 lines model, right. This is like there is a source, there is a drain, there is a gate, right. This is a transistor. Now there is one point here, and then you are drawing a kind of like zigzag on the other side. So it's kind of a register, right. So all those stuff, right, is I am taking to draw something, to analyze something and see whether it is meeting my requirement. But these things should go to silicon, right. And then when it goes to silicon, there is a process which is fabrication process. That's again a different domain of VLSI. I am not going into that, and I think some of the previous speaker of this platform have already given some introduction to that. So how to take those components, like drawn things, into a layout, right. Layout means the way it will go into the silicon with that miniaturized scale, right, from micron to nanometer scale. How it goes, how it does. So that's called layout design. What we do, we create again not a kind of like y equal to mx plus c, but we create a sort of like template, right. So this device, which is a MOS, MOS, this MOS and the registers, or the, I mean, let's talk MOS as a transistor. This transistor, resistor, capacitor, this will be having a template, fixed template. Okay, these templates we will take, let us say I have a particular device, right, and I will take that device into a drawn design with a specific template, right, and that template is nothing but which will give me the structure source, drain, gate, 2 terminal of register, right. That is called layout design. It is again very much critical domain inside analog design, right. And the thing is here, if you look at it, once I will show you some of this picture, you will see that okay, what is this drawing? I can only see some colors, maybe some a school kid has come and drawn something. Is it that thing? Is it a form of art? Yes, this is nothing but it is a form of art. The entire analog design itself is the form of an art. We are not talking about millions and billions of transistors there. We are talking about handful number of transistors, but the way we are structuring this art piece is clubbed with our intuition, clubbed with our understanding to get the best out of it, right. There are, we call in industry what is PPA, power, performance, and area. Power means how much current it takes, how much power it takes. Performance means how speedy or how much accurately it can work, right. And the area means how much silicon area, nanometer by nanometer, micrometer by micrometer it use, right. So again, today if I look at it from the point of view of area, not only we are concerned about area of this chip, we are also concerned about area in the real life, right. We are concerned about okay, how much area I have, or how much area I can actually build my house, or let us say area is always, right, we want to optimize area, we do not want to waste area, right. So area is costly, area is always costly, and especially in this particular VLSI domain, right, every small areas like nanometer scale also cost a lot. I will go through the challenges very soon. So this is the layout design picture that I was talking about. You can see some colors only in some specific pattern, but again in these colors are nothing but devices. It is a structure of a device, right. There are not thousands or millions of devices present here, maybe handful count of devices are present, but the way it is actually drawn, if you can look at it, left side versus right side, if I can draw an imaginary line in the middle, the left versus right, you can see it's almost same, it's almost symmetric, right. So that means the way it is drawn, I want to make sure that this side and that side there is no much change. When the devices are getting fabricated, I want to make sure these two guys are similar, right. May not be 100%, that is not practically possible to make any clone 100% accurate. It is not even possible, but there are ways to try to close this particular matching towards 100%, right. So that is what it is mentioned, like layout matching, symmetry, shielding. Again, shielding is one technique where we try to shield the noise, right, coming from external interference, right. We want to, what we do by shielding, I mean generally for, let us say if I want to avoid a noise, what I do, I just wear kind of like a noise cancelling headphone on my head, right, and then external noise is gone. So similarly here, what I do, I actually do a kind of a shielding through a kind of a metal line. I want to shield the sensitive part of analog circuit, right, internal, and then that's called shielding. So that's a technique in the layout, right. Layout dependent effects, these are all advanced effect. I'll not go through this in detail in this particular session, but you are free to look at these keywords and then look at available resources, and these are very interesting to learn. However, it depends on your interest. So parasitic aware layout, again parasitic, I will talk about what exactly parasitic is in a while from now. Okay. Now I will quickly take you through this design flow, right. This is the design flow that what industry overall follow. I mean the reason I am giving you this flow to let you know that let's say when you do a design, right, how you look at the design, right, you take the components, how you take the components and how you go step by step towards the end thing, right. So, the first step is specs, right. I mean, this is again very basic thing, right. I mean, let's say today you start doing, forget about analog design for the time being, you are starting doing a kind of like an activity, and that may be your anything, maybe you want to design, you want to order some maybe instrument over, you want to buy some instrument maybe. So, what you do, right, you look at what is the specifications of the instrument, what is the specifications of your mobile phone, of your tab, of your laptop. You look at the specifications, right, you list down, okay, I need this. Same thing here, you first list down what is the specification. Sometimes these specs are already defined, predefined, right, but in a new application you need to define yourself as a designer that, okay, this will be my specification that I am targeting for. Now, next step, with the specification, what you do a conceptual design. You don't directly go and then start drawing something. What you do, you, based on your knowledge, based on your understanding, you create a conceptual design, right, and you have in mind what, those components that I talked about. So, you take all those components, you create the conceptual design, write down the input and output relationships of those components and see whether your final design is meeting your specification or not, right. Again, this is what we are doing in the industry as well. It is the same kind of steps. Okay. Circuit sizing and initial analysis. Now, once the conceptual concept is in place, is in paper, what you do, you take that design into a kind of like a tool that will help you to draw those symbols, right. I have just shown you, right. Okay. And then you see whether you need to change that particular dimension of the symbol. Maybe you want to change that some parameter of the symbol, right. And then you do this analysis intuitively, right, and there will be some iterations also, and then do some analysis, check the input signals versus the output signals, see whether they are coming as per your expectation, right, and then you do that analysis, right, in this particular step. Next one is simulations, right. So, once you are done with that analysis, right, you are going into a kind of like simulation stage. Here you basically are asking the tool to run multiple simulations, right. When I am talking about simulations, why simulations is needed, right. Simulation is needed because analog design is such a kind of like a domain. It is pretty much having multiple components, right, multiple factors in it, multiple okay. I think there is a call. Yeah,
Hello.
please. Yeah.
Hello.
Yeah. Hi. Hello.
Good morning, sir.
Morning.
My name is Chandana. I am calling from Warangal.
Hi,
I have
Chandana.
one doubt, sir.
Yes.
How to select the right transistor models for analog design, sir?
Yeah. So, that is a good question, Chandana. So, how to select means, let us say, as I said, right, you have multiple devices, right, let us say multiple sort of devices, NMOS, PMOS, and inside NMOS there are multiple flavors, right. So, what you do, you, as I said, right, you know what is your specification, right, what is your end product. You need to understand, okay, this is my end product, I need this much of outcome. Will this device be sufficient? That is your understanding, right. Let us say you start with one sort of device based on your understanding and you are not able to meet it, right, in your conceptual design, right. You will again go back and look at the other device, see whether that is meeting or not. So, decision is yours, but the decision should be driven by some kind of ideas. That ideas involved device level ideas, circuit level ideas, and then whether these two things are giving you the required specification. Okay.
Okay, sir.
Yeah. So, I was talking about simulations. I need simulations because to cover all those factors, like these are multiple factors. I will talk about it in the analog design challenges section. What are the factors that we should consider? Definitely we need to run through simulations. For simulations we need tools, right? And simulations are running through the computer. Computer does the simulation with the more compute you have, you can do more simulations in a lesser time. But obviously the simulations, one suggestion is sometimes people blindly believe the simulators, right? Again, the point that we keep on telling is, do not trust simulators. Simulators is your helper. It is actually giving you a kind of like a wider picture when you cannot as a human being, you cannot imagine all those factors, right? So it is giving you some kind of hints or some kind of view, but whenever you are seeing that view, again you have to match those kind of outcome with your understanding. So here in analog design, everything is you as a human being. You have to take care of all those stuff yourself, right? So you have to understand. Again, I'm repeating the things just to make sure that you guys are having more awareness on how to prepare for this domain. This is definitely a very golden, or maybe it's like a gateway to a golden treasure, right? If you want to explore, you will definitely be amazed once you go in every day from one day to another day, right? It's like you will get professional growth, you will get your much more you will get more interest day by day. I'll take you to that a little bit more. Okay, next one is optimization. So optimization is again, like as I said, iterative process. You take a device, see whether it is giving you a kind of like the better outcome or proper outcome. Okay, no, it's not giving. Take another one or change the dimension of the device and then see whether it is happening. So it is kind of an iterative process, right? And it's actually when you are doing optimization, you take all those factors together. I will share it with you in a few time. Now the next one is layout design. Once you are done with your schematic design, with your drawing design and model design, you put it into layout, and then from the layout you come to post layout simulations. Post layout simulations are, once the layout is in place, you extract that layout into the model with multiple other components, right? Those are the parasitic components. Parasitics, we know what is parasitic. Parasitic is unwanted, right? Parasitics we don't like, but still you cannot avoid. You have to consider those parasitics because they are real, right? So what we are doing, whatever there is in the silicon, we are trying to model them, right? And we are trying to see whether I am getting the proper outcome, because once they are in silicon, right, we cannot do anything, and we cannot also do another silicon. It's like very, very costly. Okay, so this is the industry standards tools basically we generally use. This is like again stage 1, stage 2, whatever I mentioned in all those stuff. And the last thing is, if you look at it in GDS2, that's what GDS2 is, nothing but a template, is a form through which we transfer the design to a silicon fabrication house, right? That okay, take these files, these are 1, 2, 3, 4 files, right? These files we will send it to them, they will take the file, they will take in their tool, and those files will convert it into a mask. Mask is nothing but a kind of like a negative film that we have, right? I mean, if you nowadays everything photography is digital, right? But earlier days we used to have analog all those cameras, and then those cameras are getting converted into a printed view through those masks, right? Through negatives and all those stuff, right? So that's the process. Like you create those negatives and then put those negatives into the silicon as a kind of like a physical element, right? So that's what is the GDS2 means. But this is what I mean. This is just an introduction of GDS2. There are more to it. You can actually explore offline. Now, yes, this is quality check. This is one which generally we don't think, but this is definitely a very important part, right, in analog before it goes to production, right. So, we have to definitely go through these quality checks. PARC is electrical rule check. Aging is another aspect. I will take you through aging very shortly. Floating gates, right, again as I said, gate is nothing but it controls the device to turn on and off. If the device, this gate is floating, meaning there is no definition, it can take any value. So, you have no control to this device, and then this device can do whatever it wants. It can actually, it is very, very hazardous. I mean, you will be having a kind of like a design which is not working. So, you have to make sure your design is actually, you are checking this point actually in your design. SOA, safe operating analysis, right. So, safe operating analysis is one that you have to check, safe operating area. Safe operating area means where you are operating your device, whether your device can sustain that voltage drop across it, or it can break, it can actually burn, right. EMIR is another thing which is called signal integrity. Again, all these parts, right, are sub part of the design which you guys can learn as you go forward, right. Layout design flow, yes, there is a flow for layout design, and that is mentioned here. For the sake of time, I am not going through it in detail, but again I mentioned some part of it during my this discussion actually. Prototyping and fabrication is another component. Once we are done with layout, once we are done with post layout simulations, we are actually planning for prototyping, design prototyping, how to, when the design comes from silicon, I mean after silicon fabrication, right, how we test it, how we include, I mean how we interface with that design with the real time and get the outcome. We want to plan. So, we do that planning, prototyping and fabrication, validation and debugging, finalization and production, right. So, production is one thing that where we actually go for, you know, end product. The production houses fabricate with many numbers, right, and then they test each and every fabricated component. Now, when they do that testing, there are some process, there are some equipments. These are all again pretty much delicate, pretty much expensive, because again, why I am saying it is expensive, again because of the challenges that analog design has, and the challenges I mentioned, noise, environmental challenges, blah blah, all those stuff. Let us go through the challenges now. Challenges and trade-offs in analog IC design. Analog design problems. Now, this particular slide is very much, I like it very well, because this gives me a very overview of today's industry in the production house, right, how analog is making a role, right. So, if you look at it, some diagram shows that this is basically the number of spins, like let us say how much time we have to go through silicon fabrication, right. So, again going from one spin to one round to another round is very, very expensive, and as you see here, this particular data shows that the lower the previous technology to the advanced technology, there are several x or several times more expenditure. So, this production house or industry does not want it, definitely no one want to spend money for free, right. So, definitely that is not expected. And out of this survey, what we have seen that majority of the error, if you look at it, a very good percentage, very high percentage I would say, is basically from analog. And this data, if you look at it, these colors are from year to year, right. So, this is basically as we move from year to year, like recent 2022, it's still very high. So, that means that analog design challenges are increasing day by day. So, that means we have a very we need resources, we need good hands or good minds to work on analog. So, I see there is a phone, Yeah.
How to reduce noise in analog ICs?
Okay, that's a good question. Yeah. So again, noise, right? This is a parameter which has multiple angle, right? You said how to reduce noise, right? In analog circuit. You probably cannot reduce noise, but you can, you can design your device such a way it generates lower noise, right? And the other component of noise which is predominant is the external noise, right? Maybe noise from power supply, right? That's more predominant. However, there are low noise applications, low noise amplifiers, where again, as I said, there are components, right? You need to understand which component to use, right? And what should be its properties, right? So let's say if you want to have a lower noise generated from that device, right? You need to maybe increase the device dimension so that your flicker noise are going down, right? The device flickers noise are going down. But to answer your question, it's again, you have to handle by looking into those pieces, those devices properties, what will help you to reduce noise, and moreover, you should look at the external noise components, right? Where it is, where the noise is coming from. So you have to take care of that. You have to take some circuit arrangement. You have to put some circuit arrangement. You have to put some kind of, let's say, additional protection from the layout standpoint. Okay. Okay. So if does it answer your question on the call? Okay, thank you. So let's move on from this. I mean, this slide you can see that analog design still has a lot of demand, right? It's actually because the problems is increasing from day by day. So we need resources, we need analog minds who can deal with this kind of things, right? Now, design challenges. This gives you some part of it which I already talked about for analog. Now, if you look at upper value and lower value, these are the signal and noise, right? This is basically the signal range and this is the noise. So noise pretty much is pretty much at the detectable range. So we need to definitely come up with some kind of approach to reduce noise. This is the external noise, right? So make sure that your devices, you have sufficient filtering, you have you understand how to handle this noise, right? However, in the digital domain, right, if you look at it, these levels are well within the margin of noise. So we are not that much bothered about noise in digital. Now, this is a pure sine wave, this is a continuous wave, right? And then because of distortion and all, right, this particular signal, if it goes through a kind of like an analog design component and the component is non-linear, you will end up having an output which is this, right? So you need to understand how to improve linearity. There are techniques, there are ways to improve linearity. Okay. This is basically a slide that I put together to show you from analog design point of view, a very high level understanding what is parasitic, right? So this is an inverter. This inverter, when we talk about in analog, we talk about this as a amplifier, and when we talk about this as an amplifier, here is the particular region. In this region, if we operate this device, this particular structure, this amplifies signals, like V in is amplified to V out in this particular domain, in this particular region, right? This is the region, means this is V in and this is V out. V in is this, V out is this. X axis is V in, Y axis is V out, right? So, and this is the region where the devices both are operating in saturation. Now, saturation is, again, these are the things that we need to understand. What is saturation margin, what is saturation region, and what are the other regions at which the devices will work, right? There are some requirement for that, and definitely I think I have some more understanding on that. So here, these components that you see in red, these are parasitics, and these are coming when the device is getting manufactured, right? Now, there is a capacitor coming between the input and output, there is a resistors coming between the power supply and this net, there is another resistors coming between these two nets. So, if you do not consider this, right, what will happen? This particular characteristic, you think that this is related to this one and you are not considering these three, these components, this characteristic will change, it will not be the real characteristic. So, what you are doing is you are not considering the real factors coming out of parasitics, right. So, you definitely have to have this understanding in your when you are designing circuits, right, that what is this parasitics, where the parasitics will come. Yeah, there is a question.
Hello, sir.
Hi.
Hi, sir. I'm Shiva. I've done my BTech in Electrical and Electronics. So last year I've done my PG diploma from CDSI, that was in embedded systems. So now I want to move into the analog design part. Like, how should I get into these things? Like, should I do an MTech or should I visit any training institutes? Or I'm not getting the right path to get into this role.
Got it. Yeah, sure. I'll be happy to answer it. Sorry, I could not understand the center that you have done embedded systems training, but again, when I started this discussion, I mentioned, I have given a small story of my case, right, as a story. So what I have done is from BTech to masters, and from masters I started the journey, right. I did my project in analog, and from that only I have get into the industry. But in your case, right, you have done some embedded systems, right, but depending on your depth into analog, right, my suggestion would be, in this case you can actually go through some kind of, let's say, there are a couple of things. Maybe you can go through some of the training institutes where they take you through or they will help you to bridge that gap between what you have, your theoretical understanding on analog versus the practical part of it, right. That's one thing that you can get into such kind of institutes. There are multiple institutes, and the other one is you yourself can learn. There are several open lectures, there are several things right now available. Internet is very easily available nowadays. You can do it yourself, and then again do some kind of project, go into an internship, right, and then do some kind of internship in the industry. May not be the tier 1 industry, maybe some startup and all those stuff, right, and then based on that you can get into the analog field. So in order to go into the analog, what you have to do is you have to learn analog first. You have to get all the basics clean, right, and then do some hands-on, maybe through an institute that gives training, right, or through some internship. Okay, so going back to my slide, so this is a design challenge, which is process variation. Now this process variation is predominant, right, for analog. If you look at these diagrams, the center one is that particular IC, this integrated circuit, the wafer or silicon wafer, and inside this you have all the small boxes, they are all chips, right. Now these chips are spreaded across the wafer, and there are multiple wafers, right, wafer A, B, C. Now these wafers, right, if you look at the distribution of the components, right, let's say x-axis and y-axis, x-axis is NMOS and y-axis is PMOS, and the threshold voltage of NMOS and PMOSs, right. So you see there is a distribution here, right. Now this distribution talks about the process corner. There are multiple process corners. One process corner is here, another process corner here, another process corner here, and then there is distribution. Now we talk about global, we talk about local distribution. When you talk about local distribution, we go into a single corner and there are kind of like multiple variations, right, here. These variations are device properties variation. The threshold voltage, the beta factor, whatever the during manufacturing, right, all those things are getting changed. So then what you have to do, you have to consider all those changes. There are models from foundry, from the manufacturing house, they provide the models. We have to take those models, check our designs how they are performing, whether they within this particular simulations, running the simulations within these corners, we are able to meet the specifications or not. Okay. So, now you can correlate, right, from, let us say, starting from devices understanding, circuit understanding, and then how these devices are getting manufactured, what are the impacts. These impacts are very, very dominant when you are talking about analog, right. Digital also it has an impact, right, but digital impacts are in a more crude way, but if you look at analog, these impacts are more finer, and you have to make sure that you take care of those impacts, take care of all those factors to get a better yield, right, better yield of your manufacturing. You should not be, let us say you are manufacturing 100 units, right, out of the 100 units you should be I mean the designer I mean the final aim is to get 100 out of 100 properly working. Now, if you are not considering these factors, maybe out of 100, 70 will not be working because these are outside the boundary, you have not considered that, right. These are design errors, and those design errors, if you look at it, if you remember few slides back, I was showing an industry survey report. It is showing that design error is one of the major cause of these multiple spins, right. So, this is very, very important, guys. This understanding is needed from you if you want to go into the analog side. Now, again, some design challenges related to operating point, saturation, operating point, linear, and then cutoff. These are all basics, and in fact we need to understand that, and here are the things which you have to make sure that these ideas are into our veins. It should flow in our veins, right. We will be dealing with this every day in and out. Okay. Going to the next one, this is very important slide from an analog design standpoint. This talks about trade-offs, right, trade-offs in analog design. There are several entity: power, noise, layout, gain, offset voltage, process variation, load driving, stability and compensation. I talked about noise, I talked about layout, I talked about some part of gain, offset, process variation, load driving, and all those factors. Now, if you look at this, these are all interconnected, guys. If you try to improve noise, you may end up consuming more power. If you try to reduce power, you may end up having an unstable system, right. If you actually try to improve maybe offset, you may end up having more area, right, which is layout, right. So, these are the factors. I mean, if you look at it, analog design is pretty much like you cannot have majority of thumb rules, right. There cannot be thumb rules. It's like design from your intuition, from your ideas. You have to sleep over it, you have to live over it, you have to work with it, you have to talk to it. You understand what I am trying to say, right. Now, if I want to go into all these details, it will take again hours and days and months to discuss, right. So, I leave it to you, but I am just trying to give you a general overview and perspective of what analog design trade-off is. This is again what I am talking about in terms of matching and layout techniques, challenges with layout techniques. These are for further study, guys. I am just leaving it to you. Real world consideration, temperature compensation. Now, in this temperature compensation, again, temperature is an environmental factor, and why temperature is important? Because anything, if you run through, right, you see when you are continuously talking over phone, what is happening? Your phone is getting hot. That means it is actually due to the power consumption, due to the continuous operation, it is getting hot, right. So, your phone is getting hot means your devices are also getting hot. So, you need to make sure that even though there is a change in temperature, I mean definitely if there is a change in temperature, the device characteristics has its own things, right. I mean device won't work in the same way, it will change its properties, right. So, overall if the device properties change, your circuit properties will also change. So, you have to make sure that even though the temperature of the device is increasing, right, the performance is not degrading much, right. Otherwise, you cannot control the things, right. This is one example, but think about some extreme cases, right, where we talk about higher temperature zones, right. I mean huge extreme temperature zones. They are also, your circuit should operate, it should not degrade, right. If it degrades, the entire system will fail. So you need to make sure that your circuit, some part of it has a thermal temperature compensation in it, right. And how you do that compensation? You balance the temperature coefficients. Maybe one device is having positive temperature coefficient, another device is having negative temperature coefficient. You combine both of them in a very balanced manner to have a flat temperature coefficient, right. Meaning with temperature change, the characteristics won't change, the device performance won't change. Okay, it's again kind of like balancing act, right. And we do it every day, right. We try to balance things in everyday's life, right. I mean, if something is going up, we'll try to put it the other side down, right, so that overall our execution we can live happily, right. So real world consideration, this is another thing as we go from as we are advancing from the technology, VLSI technology, right. Today we are talking about nanometer scale, we are having better devices, we are having advanced devices which I have shown you, like gate all around device, right. So these devices have been incorporated to improve performance, right, like speed, performance, the latency time and all those stuff. But these are coming not for free. This will have definitely some other impact. One of the impact is reliability, right. The reliability is a factor, meaning once you operate those devices over the time, those devices will degrade its performance, right. It will definitely have to degrade. So there is a kind of like a bathtub tub. Is there a question? No. So there is a bathtub tub here. This is pretty much true for not only for semiconductor or not only for analog, but for everyone. So this is the failure rate versus time. Infant mortality at the beginning when we are doing the production. Useful life is when the design is in production, is in use, and then after some time we have to throw the design out, right. So our target is to make sure that the useful life is extended, right. Any design, any kind of product that we are going through, we have to make sure that the useful life is extended, right. Maybe 10 years, 20 years, right. The more we can use, the more we can, the more value we are getting in, right. So specifically if you look at the medical instruments, right, the say for example the pacemaker and all those stuff, right, definitely doctor doesn't want, or probably we don't want to get it operated every 2 years, right, and change the device. That's not what we will be looking for, right. So in order to do that, right, burn-in A to B, how to improve burn-in in A to B, how to improve useful life B to C, there are ways, possible actions that we have to take, and this we take across for analog design as well. There is a flow how to take care of that particular thing. Now there are some phenomena, right, HCI, TDB, TDDB, NBTI, PBTI. So these are the phenomena and these are related to the devices. I would suggest you guys to read through it, understand what are them, and then while you are taking them, right, in your design, you just have to understand them, see the implication, and then go through some kind of checks, right. This is again some simulations you have to do. Finally, you check with the simulation, right. Let's say the simulator will give you outcome of a from a stressed netlist, right. There is a stressed netlist. Now what is netlist? I think I should give you some understanding. Netlist means it's a kind of like model, like you have small device models. Now you connect those models and then you form a bigger model, right, of the entire circuit, right. So that model is actually connected, I mean one model to another model in a kind of like a kind of like a form, right? So that form is nothing but the netlist. Now what the tool will give you is a fresh netlist and another is a stressed netlist. Now this stressed netlist is actually stressed over the period of 10 years. You don't have to wait for 10 years. The tool will does it. Tool will apply some intelligence, maybe like artificial intelligence. Nowadays it is much more there. Yeah, I'll just take a call. Just let me finish it. So with this particular stressed netlist, we will run through the simulations and we will see the impact. Yeah, let me take the call, please.
Hi, sir.
Hi.
I'm sure, sir, from previous call. Actually, can hear. So the doubt is that, like, I've seen some institute, but they're offering analog layout design, so analog layout. Is it the gateway to enter the analog design part, or can you name any institute for analog design, if you don't mind?
Okay. So analog layout, it's a domain, right? It's not a kind of like you can treat it as a gateway to enter into analog design. Definitely, if you are coming through any kind of, let's say, opportunity, right, through an institute, you can take it as a choice, definitely. But I mean, if that is not the case, right, and if you want to go into analog design, as I said, the process, the best process is to train, is to get into kind of like a training institute. There are many training institute, I mean, across the country. You can, I mean, the one that I know, I mean, very much I'm associated with is VEDA IIT as a training institute. You can explore that also, but there are several other things. Okay, that's because I know I am very much close to it, so I am just having a name for you. But yeah, I mean, analog design can be a gateway into analog field. However, the first thing that you have to develop is your understanding, device understanding, circuit understanding, intuitive approach, how to look at things. Okay. Did I cover it? Okay, thank you. So let's move on from this one. Implication of technology as advancement, right? This is another thing that we should know is how, I mean, I was telling you some part of it, that once we are moving from one technology to another advanced technology, what are the implications are coming? Obviously, we are going to a new technology for something good, right? And something good is smaller geometries, because going to the smaller geometries means higher density. We can actually have the similar performance or a better performance in low area, right? And the area is critical there, right? Yeah, another call. Okay, go ahead. Why? Hi, can you please come again? Hello? Hey, can you hear me?
Yeah, hello.
Yeah, go ahead, please.
Yeah, hello.
Yes, I can hear you. Go ahead.
Yeah, hello, sir.
Yes,
Hello?
go ahead. I can hear you. Please.
Yeah, sir. I'm 𝗂𝗽𝗺𝗺𝗃𝗧. I'm a research scholar from Calcutta University. So, sir, actually, I'm also doing my research on analog design, analog domain. My query is just a few minutes back, you were talking about the reliability issues. I just wanted to know, when I'm sending my design for fabrication, can I perform the reliability issue, I mean, prior fabrication, or it's a post-fabrication thing that you are suggesting?
Got it. Yeah, that's a good question. In fact, you have to make sure that you are covering all the reliability aspect before fabrication, because once you are after fabrication, right, you cannot do much, right? And the reliabilities are coming as impacting your device performance, right? So you have to take care of it before you put it in a silicon.
Okay, and sir, since we are using, I mean, ACL PDK thing we have, so what are the tools that you are suggesting for analog design? I mean, before fabrication that we can run for reliability?
Yeah, there are industry standards tools. You can, I mean, I don't have anything specific in mind right? Any tool is good enough, but again, before you are utilizing the tool, you need to make sure that the models that you are using, right, from the foundry house, right, it is actually certified, right. Let's say the tool that you are using, it is certified, right. It should support. Any tool is good, but the model should support the tool.
And so for that purpose, do we need to talk to the the technology unit itself regarding the reliability issue so that we can handle that?
Yeah, I think if you are, let's say your design is very much sensitive towards the reliability factors, it is coming under stress, right, and you are taking reliability as one of the critical thing, right, definitely it is advisable that you should talk to the relevant folks, right, who gives you the models, who deals with the tools, right. You should understand that. Yes.
Okay, sir. Okay, sir. Thank you.
You're welcome. Thank you. So let's move on. So what is good? Good is this: smaller parasitics, higher transconductance, higher bandwidth. What is bad? Bad is reduced voltage. This is another thing. Once we go from one technology to another technology, reduced voltage means power supply voltage, it's scaling down, right? And then power supply voltage is scaling down, but the threshold voltage of the device, after which the device work intentionally, right, that threshold voltage is not scaling down. So you actually end up having more challenges day by day once we are going from one technology to another technology, right. And that's why you are seeing more failures, right, which is originating from analog, and that's the reason we need more experts who can deal with all those additional factors going forward. Okay. So if you see the bad and the ugly, these things are more once we go from technology advancement, we take the technology advancement in our design, right. So we need to consider this more. Okay. Case study and practical application. Now I actually want to take you through some of this case study. It's not possible for me, for the sake of time, to show some design in hand and then how the design is structured and all the stuff, but let's see how the things are. Let's take an example of a low dropout regulator, right. Again, why it is low dropout regulator, right? It's kind of like a kind of a segment or a small block inside the power domain, inside the power management. I have shown you power management, right. Inside power management, you have low dropout regulator, which is actually giving you an output voltage or a kind of like a voltage source that actually can be used to deliver power towards the core, towards the analog core or digital core. Another call? Okay, I'll hold for another call. Yeah. Hi, I can hear you. Go ahead.
Hi, sir.
Hi.
Hi, sir. How does the power supply noise affect the performance of an analog circuit, sir?
Power supply noise
affects the performance of an analog circuit.
Okay. How does it affect? Okay.
Yes.
So, okay. How does it affect? It would have been good if I can have a board and all, but anyway, let me try to explain. So your power supply noise, right, if you have a kind of like high frequency noise, right, at the power supply, what is happening in your design, like between terminals, right, as I have shown you, there are components, right, let's say parasitic components, right. Those components are capacitors. Those capacitors are actually there, although you are not able to see this in the model, but you have to visualize that and you have to consider that's a component. So that parasitic capacitors are present. Now that high frequency noise in the power supply through the capacitors are having a low impedance with high frequency noise. So that high frequency noise will actually come and it will actually impact your output. So let me, I was about to come to that anyway. So if I show you this particular diagram, right, this diagram is actually the input voltage of the regulator, and this is the output voltage of the regulator. Now, if there is, this is the power supply, right, if there is a noise here, right, this noise is actually getting to the output, right, through a capacitor between this and this, which is not drawn here, but it is there. It is there as a parasitic. So, you have to make sure that you are envisioning this capacitor and take some steps to reduce this noise, right, from here to here. So, either you add a kind of like a filter, or you structure this particular device such a way there is a less coupling from here to here. Okay. So, that is how, I mean, maybe this can also be used as a kind of a filter where the noise can go out. Okay. So, this hopefully it will give you some kind of hints on how to handle it. Okay. So, moving on to the slides, let us say what I was talking about is LDO. LDO is used for delivering a steady power supply to the internal core inside a chip, right, and it is pretty much there in every system on chips, right. LDO is used in every system on chips, right. So, LDO, here are the specifications. As I said, any design will start with specification. Here are the specifications that has been tabulated, right, and here are the design. This is the conceptual design that someone has started with. He knows or she knows that, okay, if I use this particular diagram and if I start with this, I should be able to achieve this one. May not be, I do not know at this stage whether I will be getting 300 millivolt, but I will target to have 300 millivolt, and fundamentally this structure can help me, right. Now, again, look at this plus and minus, how they are connected. This is very important, because if you swap this plus and minus, you may not be able to get a stable system, right. So, as a designer, you should know how these structures are connected, right. Again, as I said, in the final design, when you do the design, you also need to cover these additional components like the parasitic components. There will be a resistor connected here, which is there. However, you cannot envision that, because I mean, that is not in this particular model. Once you do a post layout simulation, that time you will see these resistors, these capacitors. Now, there will be another capacitor here that will add additional poles and zeros and all those stuffs, right? Like poles, zeros are again coming from controls, right, control theory, right. We generally study those theories also in our academics, right. So, that is the design consideration. Stability, compensation, we should consider that. We should also take care of overheating. I mean, definitely if this current that is flowing through this device is very high, right, this is the load, right. This load can be a big core, right. A core means like a digital core, maybe high speed core, it is actually operating here, and this output is actually delivering current to that core. Maybe there are hundreds of milliamps of current flowing through this. So, that will actually create a lot of heat, and that heat can actually impact this device performance. So, you need to take care of that heat dissipation. You need to work on thermal management on that particular side. Okay. So, again, this is the power efficiency. I mean, there are some equations. The equation is somehow it is not properly added, distorted, but note that these are the design considerations, like in order to get an efficiency, a better efficiency, what are the design consideration we have to take care. Okay. Applications of LDO are power supply for analog and digital ICs, battery powered devices, noise sensitive applications, because we want to, let us say, if I mean, I have a particular block which is very much noise sensitive. So, instead of connecting the block to the main power supply which is coming from an external world, what I want to do, I want to take the power supply, take it through an LDO, and then create a power supply which is much stable and flat, right. It is not having much disturbances, and then I give it to the noise sensitive component. So, this is another way to handle it, but obviously that will come with additional cost, obviously. Yeah. Question is there? Okay. Emerging trends, I will quickly take you through the emerging trends. Emerging trends, right, in analog design. So, some part of it I already mentioned. As you see that from the survey, I will go back to the same survey which I really like. Now, that survey says that I mean, from year to year, I see more and more analog related failures, right? I mean, design specs are not properly identified, or there are some analog errors, and that cause a lot of SOC failure, and that is like respin and all those stuff, right? So that's the trend. I mean, this will continue because right now the devices are I mean, whatever equations we learned in our books, right, empirical equations, they are no longer following those equations. So the devices are completely new, the devices architectures are completely new. So we need to basically deal with that part. That's the trend. I mean, going forward, we can't do anything. I mean, devices are devices. Now we have to come up with some good circuit techniques to deal with those nonlinearities, those challenges, right? So there is a huge scope, or probably we are going through it every day, as I said, right? So there is a huge scope for more and more opportunity to invent, to explore, and to do a lot of like innovation, right, on this particular domain. Now all of these things are coming for downsizing, energy efficiency, and performance improvement. These are always be there, right? I don't want to specifically go into some part of it today, but this is the main thing. Downsizing will always be there, right? Power efficiency, energy efficiency will have to improve, and then performance improvement is always the card, right? Now AI and machine learning. So this is another buzzing words, right, that we talk about AI and machine learning, and our EDA, EDA means electronics design automation vendors, right, the tool houses, right, they try to incorporate all this AI and machine learning techniques to improve the analog design flows, methodologies, right, and incorporate all those things, right, while I mean right now all the simulations, reliability or corner related simulations, right, they incorporate this particular machine learning or AI, and then make it much more effective and closely related to the silicon. So silicon and simulation correlation, the better you can do, the chance is better to have first pass silicon success, right? So that's where the AI and ML in the future, guys, are, I mean, there is a trend that okay, incorporate these techniques into the tools and make the tools much more effective, where the tools can take the silicon factors well ahead of the production. Emerging trends in analog design, technology drivers, right? So what are the technology drivers? One of the thing is 3D integration, right? 2D we can't make much, right? There is a limit. Now we are going to 3D. Now 3D means like one on top of other, one wafer, another wafer, another wafer. It's a kind of like multi-storied building, right? Instead of having the buildings in a single floor, we construct into a multiple floor. So in order for to do that, there should be techniques to handle the signal flow from one top to the other floor, one floor to other floor, right? So all those things, I mean, definitely those are adding additional challenges, right? Advanced computer aided design CAD tools, that's also the technology driver. Analog to digital, I mean, this is integration of analog to digital circuits together into a single place. Even there are some of the technologies for a high speed communication today. When we talk about it, there are chip to chip protocols, right, which are sitting very close to each other, right? Maybe these chips are in a different platform, but they work together for a unified solution, right? So that's called UCIe, kind of like an approach or application. Now mixed signal system on chip designs, right? These are the drivers for the analog design. Skill required. So here I would like to spend some time. So throughout this discussion or throughout this session, I have I touched that point, that what an analog designer, what should be the thinking process or visibility, not visibility, probably I mean how I can take this analog design as my career, right? What skills I should develop, right? And how I can start looking at it, right? So requires an ability to multiple concepts simultaneously. So again, as I said, right? So take an example of this jigsaw, which I again come back to the same thing, right? Jigsaw puzzle, right? When we have all these components placed in a single area, like they are all in multiple places, what we do, we actually scan through them and see how to handle them, right? So multiple concepts are actually here and there, and now we want to see how to take one first, then this one, then that one, and then put it together to a proper form, right? Make appropriate simplification and assumption. Now this is another thing that we have to, I mean, as an analog designer, it is definitely needed, that how to simplify the things, right? I mean, one can look at a single inverter, NMOS and PMOS, in different way, right? I mean, it's that intuitive approach you are taking to look at a circuit, right? Maybe an operational amplifier which has multiple components connected together, how you are looking at it, right? How you are looking at the signal flow through that operational amplifier, and then finally you understand where the pole is, where the zero is, how the poles are getting into the operation, right? So that, I mean, because there are so many factors connected to it, right? There are so many components, you need to conceptualize those components and put it into your understanding, rather than always try to, I mean, sometimes I see, right? I mean, that's the nature. I mean, when we study a book, right, we study the equations, okay, we try to recollect the equation and then try to put those equations into the device, right? And then end up, I mean, once you try doing it, right, there are multiple devices, there are multiple parameters, equations, and then you will not be able to resolve that, right? So must have good knowledge of modeling and technology, be able to learn from failure. This is one thing that we definitely need. Be able to use simultaneous simulators correctly. Again, this is the point which I am telling, that simulators are our helper, they are not dictators, right? So we need to handle them, we need to handle the simulators, we need to use simulator properly, we need to understand what are the knobs, what are the parameters for the simulator, right? Let's say there are multiple options through which you can control all the settings, right? Accuracy settings, speed setting. Now you want to understand how much settings that should be, right, for your specific circuit, right? Analog is again discrete, I mean, not like the digital, which is like done with respect to some fundamental gates, right? That is a different thing, but analog is totally customized, right? It's like one amplifier to another amplifier, it's different because the specifications are different, right? And you are always trying to derive a solution which is particularly meant for that purpose, with optimized outcome, right? With optimized power, optimized performance, and optimized area. So that cannot be same, right? Although, I mean, two applications, two requirements, two specifications, you cannot use a single amplifier, right? Because either you are doing an over design or under design. Okay. So with that, I am about to conclude this session, and then couple of takeaways. Analog IC design, yes, as I said, it's a critical field that combines creativity with problem solving. Again, I already mentioned, yeah, there's a phone. Yeah, go ahead, please. Hello.
Hello, sir. Good morning, sir.
Morning.
I am Runasi from Secunderabad, sir.
Sorry, what's your name? I could not get it.
Hello.
Yeah, come again, please.
Hello.
Your name?
Sir, I'm Runasi from Secunderabad, sir.
Rona.
Runasi.
Okay, go ahead. Yeah, hi.
Sir, I have some doubts, sir. What are the topics, important topics to be prepared while attending analog design technical round, sir?
Yeah, I think some part of it I covered. Let me repeat. So let's say when you are going for an analog interview, right? I mean, what we look at from a person in that interview, we basically look at how the person is looking at not designing a circuit but breaking a circuit, right? We see how he is looking at a circuit more simpler way, right? So let's say I just given an example, right? Let's say you have a two-stage amplifier, right? We actually see if the person is looking at the circuit in a kind of like more theoretical ways, try to draw something like maybe creating a complex model and then explain something, or he or she is trying to look at the circuit from a pretty much in intuitive fashion, right, and connect the small blocks, understanding maybe a device understanding, and two-stage amplifier is nothing but a differential amplifier, maybe one active load, understanding the differential amplifier and then connection of that understanding to the next stage, right? So we want to see that in that way, right? How he is looking at a design more intuitively, right? Whether he or she knows where the design will fail, at what is the fail point, right? That's what we wanted to know. So to prepare for an interview, you don't have to be champion on everything. You be focused on something, but try to understand that particular topic end to end. Okay. So going back to my conclusions here, this is combining creativity and problem solving, and students to embrace the challenges and opportunities in this external. This is what I always encourage, that okay, do not get fear of it, do not get definitely there is nothing to fear, it's only your intuition, your interest, and you are working in it, right? So so please do that one and proceed on that particular line. Okay. And the other thing is, as I said, that in order for you to get into this, there are definitely whoever is right now on the course, try to have internship from the from multiple design houses, get into the real or maybe take a project where you do a design with the real time specifications, right? Maybe some specifications, some kind of things may be very fancy, right? But those things may not be properly that may not be needed as a wider application, right? So focus on those things where, let's say, the challenges that I mentioned, right, today we are seeing for the analog design is much more efficient area, power, solutions and all, right? So focus on those particular lines, may not be everything but very focused points, and yeah, that should be good enough for now. Yeah. Any further questions? Anything? Yeah. So if nothing is there, I think we are good for today. Again, this is one more snippet on skills needed: strong fundamental foundation in circuit theory, semiconductor physics. Definitely we don't need to be a champ on the semiconductor physics, but definitely we should know that. EDA tools understanding, high level understanding is good enough. Importance of internship and projects and analog design, recommended resources and certification to explore further. With that, thanks to all for attending the call and attending this session, and really it gives me a lot of pleasure to be a part of this initiative by TASC, by Government of Telangana, and I am very much encouraged on this particular initiative, and all the best to all of you. Have a great day. Thank you.